So continuing our intermolecular forces talk, we're now going to focus on boiling point. Just to refresh our memory of boiling point, here I have a crude thermometer right here, and right now it's in liquid form. So, in general, temperature is movement. So if the temperature is high enough at this point to be a liquid, then they're going to be moving around each other. But the intermolecular forces are still keeping them close to each other. As the temperature rises to the temperature of the boiling point, that's when the intermolecular forces are overcome by the movement of the molecules, and they just fly out of the beaker. Well, they should be flying. Instead, they're not doing anything. There you go. So then they're just flying out of the beaker, boom, and they bounce against things, and voo, they go off and disappear into the great blue yonder. So, going back to the slides, in this case, there are two ways to increase the boiling point. One is by adding in a functional group, which increases the intermolecular forces. The other way is, and that's something we'll talk about a little bit later, is to increase the overall size of the hydrocarbon. And by increasing the size of the hydrocarbon, we can actually increase the power of the London force, and therefore increase the intermolecular force, which increases the boiling point. In this example right here, I have the functional groups added to the hydrocarbons, and essentially the more powerful the intermolecular force that we ranked earlier, then the higher the boiling point. So ionic is on top, hydrogen bonding, and then finally we have a tie for these two molecules which exhibit dipole-dipole forces, and then on the bottom we have London forces. As I said before, it's possible to have more than one intermolecular force in the molecule, so we're going to focus on the dominant intermolecular force. I also just said right now that if we increase the size of the hydrocarbons, we increase the size of the London forces. But I don't want to sit there and confuse you. So if I give you these as examples, I'll always try to keep the same size hydrocarbons. In this slide right here, I went ahead and I added in an exception, and I showed you a nice decane molecule right here, showing that if you increase the size of the hydrocarbon, you increase the London force, which increases the boiling point. But I want to point out, I'm not going to give you a question like this where I combine size of hydrocarbons and functional groups. So in this case right here, we'll just compare functional groups or the lack of functional groups, and you'll have to rank them, which has the highest boiling point. I also want to point out that when it comes to alkenes, alkynes, and aromatics, they're roughly on the same level of intermolecular force, so therefore they have roughly the same level of boiling point. Let's go ahead and see examples of this in our ISIS. So in this case, let me go ahead and open this up. Here we have examples of pure substance molecules. I'm not going to give you mixtures and ask you to do the boiling points, but pure substance molecules. I guess I should have just drawn one and just said it's pure substance, but I saved you the whole visualization time. So in this case, here's a pure substance, and I just happened to duplicate the molecule next to it. And in this case, the top one are ionic forces, hydrogen bonding, various examples. In short, the stronger the intermolecular force, let me highlight this. The stronger the intermolecular force, the higher the boiling point. So ionic is on top, and if we keep going down, you see hydrogen bonding followed by dipole-dipole. Then we see typos. This should say dipole-dipole. This should say down here for these typos, real-time error correction, by the way. It should say dipole-dipole, and then these are London down here. So the weakest functional group also have the weakest boiling points, or the lowest boiling points. And the strongest, highest polarity functional groups, such as ionic forces, therefore have the highest boiling points. Let's go over to here. Now, hydrocarbon size is also a factor. So, in this case, the larger the hydrocarbon, then the higher the boiling point. Going to slide 11, we see a nice worked out example here where we have, in this instance, the lower or the smaller hydrocarbons, and then on the top you have the bigger hydrocarbons. The book sometimes makes reference to molecular weight. So if they say low molecular weight molecules, are referring to not having a lot of hydrocarbons. If they refer to high molecular weight molecules, then they're referring to molecules with a lot of hydrocarbons. So direct relationship between size and boiling point. Don't forget branching. So I included this as well. It turns out the more branched it is, then the lower in boiling point. So let's compare these two that I'm circling right here. In this case, the one on bottom is more branched, even though it has the same number of carbons and hydrogens, so it has a lower boiling point. Now, as the sheer size of the molecule gets bigger and bigger, even if it is branched, if it has more carbons and hydrogens, then it will have a higher boiling point. Essentially what happens is, if we were to think of these molecules right here as being on water, and let me go ahead and draw this out really quick. Let me go ahead and pick on one of these. If we were to sit there and think of these as being on water, I just said that. I want a nice example, but it's not working right. Aha! I finally got it. So let me go ahead and dig all this stuff away to the side. I'll repair it later. There we go. Again, if we think of this molecule as being on a layer of water, the longer the boat, if I were to sit there and be on top, and I were to sit there and start rocking the boat and going back and forth, there'd be much greater rocking motion. It turns out on a molecular level, a rocking effect occurs when it comes to electrons. So the longer the hydrocarbon, the more the electrons will sit there and they'll rock backwards and forwards. So in this case, I'll go ahead and I'll use a yellow pen. In this case, the more rocking there is, the more the electrons will sit there and rock backwards and forwards. Now I'll use a red pen. The longer the hydrocarbon, the more it'll rock backwards and forwards. The more it rocks backwards and forwards, the stronger the dipoles are. The stronger the positive and negative dipoles on each of the sides of the hydrocarbons are going to be, and therefore the higher the intermolecular force. So what this means in practice is, if I have a molecule that looks like this, this is a big molecule above 10 carbons. There's so much rocking that the intermolecular forces for London forces increases so much that this would actually be a solid. And the London forces can become so strong that they can actually rival the functional groups of more powerful intermolecular forces, such as ionic forces. So therefore, if we went back to slide 10, we could see that the decane intermolecular forces, even though it's London, can compare and rival the ionic forces. This is also the reason why branching cuts down on the rocking. So for example, this molecule right here, if we compare this one that I just circled with this one, even though they're roughly the same size, this has a lower boiling point. Why? Because it's harder to rock it backward and forth. Therefore, less rocking of electrons, less dipoles, temporary dipoles, and then less intermolecular force, lower boiling point. If you understand that, great. If you don't, I'm not testing you on this rocking theory. But some people were asking, so that was my lame attempt. Going back to the ISIS, so in this case, here we see a very, very large molecule, so it has a higher intermolecular force. Here we see a cycloalkane, still really large, so second. Therefore, these are the ranking of the boiling points. As we keep going down, smaller molecules, smaller boiling point. And then as we keep going down, we see examples of molecules that are substituted. So this one right here, if it's more substituted, it'll have lower boiling point due to this less rocking motion. So you'll be responsible for understanding and ranking boiling points of functional groups and hydrocarbons.